to start the design equations for continuous reactors. So, in our previous class we have discussed or developed the general mole balance equation, and then we have developed one design equation for the batch reactors. So, now we will start continuous reactors. Continuous reactors, so those are we have studied that is the CSTR reactors, continuous start tank reactors, or you can say it is CSTR reactor. So, these CSTR reactors, plug flow reactors or packed bed reactors. So, these are the reactors. So, are called continuous reactor or continuous flow reactors. So, these are the reactors one by one we will consider, and then we will develop the design equation for each reactors. Okay. So, we know the basic general mole balance equations that we already have discussed in our previous class, or we have developed. F j 0 minus F j plus rate of generation part integrating R j d v equals to d n j by d t. So, this is the general mole balance equation. Now, we will consider start tank reactor or continuous start tank reactor, CSTR reactors. So, in this particular reactors, when we will conduct any reactions, means in this particular reactors we have chosen this particular reactor, let us say this is our reactors. So, if we conduct any reactions, let us say A plus B going to C plus D. So, we have to charge A and B over there, and then we have to maintain some temperature or pressures, and then reactions will continuously carry out or work will be there. So, here stirring is there. So, this is stirrer is there, continuously stirring operation should be there, means mixing should be there inside of the reactor. So, if we in this type of reactors, if we take samples anywhere inside of the reactor, the concentrations rates throughout the vessels or the reactors would be the same. So, therefore, anywhere any points, so you can get the same concentrations as well as temperature concentration also. So, this type of reactors we can means consider, and we can develop the design equation for that type of reactors. So, here if we consider at the beginnings when the reactor we have reactions we have started. So, then there was no accumulations, means the reactor was empty, let us say this is empty reactors at the beginning. When reactant is feeding here, so reactants let us say A is coming. So, that would be fill up, means initially there was nothing. So, after a certain period of time, or to fill up that particular specified volume, so it reactants will be accumulated over the reactor. So, then once the reactors will come into steady state, so there is means the amount reactants will inside of the reactors, the same amount will be leave from the reactor. So, then temperature maintain will be there, continuously reaction will carry out for that particular reactors. So, in the type of reactors, if we say that there is no accumulation part, means if the reactor is under steady state operation, that at steady state the accumulation part is 0. So, then this part d n j by d t for species j we can consider is 0. Okay. So, then this part we can eliminate. So, here inlet is there, outlet is there, and inside of that reactor. So, when reactant will charge, maybe the reaction may be multiple step or multiple process are there, multiple step the reactions may be carry out. So, then some of jth component may be formation is there. So, that in terms of rate of generations would come. So, now these equations we can express this way. Okay. So, after integrating within this total volume or system volume F j 0 for jth components minus F j equals to minus R j rate of formation of the j into V. So, these equations we can rearrange. So, rearrange we can get V equals to F j 0 minus F j by minus R j, that is the design equations, means for a CSTR reactor. So, here these equations we can express for component A, V equal to F A naught minus F A by minus R A. This is the design equation for a continuous start tank reactor. So, these design equations whenever it is required we use, if we know inlet entering molar feed rate and exit molar feed rate of the reaction systems. So, then we can find out the volumes is required for that particular reactions at that rate, specified conversions if you want to get. So, then what volumes of the reactors we have to use, that will find out or using this particular design equation if we want to conduct that particular reactions using that reactors. Okay. Now, we will discuss about plug flow reactors. This is another type of reactors I said. So, this is also continuous flow reactors or tubular reactors you can say. So, here its a diagram is shown here. So, this is a plug flow type of reactors. Here reactant is feeding here and product is coming out here. So, here means from left side to right side if you move means reactants will move from left hand side to the right hand side and reactions will take place within that inside of the reactors. So, this type of reactors there is no stirring or stirring operation is not there. So, reactants will in and that what is the form means reactants will be converted into the products. So, that will be come out and if there is unreacted reactant that also will leave with the product stream. So, here along the length means if we move from left hand side to the right hand side this is the total length or total volume of the system. So, you can see that the concentrations of that reactants. So, here I said let us say is the our reactants. So, concentration of the reactants along the length that will vary along the axial direction throughout the reactor. So, every points if we consider, so the concentrations will be different individual points. If individual point concentration is different, then the rate of the reactions would be the different along the axial directions. But we are assuming that in the this is the radial directions or radial position. So, everywhere radial direction there is no changes of concentrations or no conversion changes or rate changes along the radial direction, but axial direction from left hand side to the right hand side conversions as well as concentrations or that both will vary along the axial directions. Okay. So, for that if we want to means develop a design equation for this type of reactor. So, then we have to consider a small element of volume for spaces J. So, this is the small element of volumes we are considering. So, within this, so here's a small element of volumes and rate of generations delta Gj for that component J is considering within this particular volume is this, and at this particular point let us say within this small volume Fj that is at that particular volume when their reactant molecule entering, so we are expressing Fj and this particular points we are expressing V plus delta V, that is the small difference is delta V within that particular one position to position this position to this position the changes of volume that is the delta V, very small elements. So, within that if we consider, so here's the general mole balance equations we already have discussed. So, here in this type of reactors also there is no accumulations. So, if the reaction or system is working or operating under steady state, so then dNj by dt we can consider as a 0, this part we can eliminate okay, from the mole balance equation, then rest of the parts would be leaving theirs. And then if we divide the plug flow reactor into the I said into the n number of small or sub volumes and each sub volumes is the differential volume that is delta V. Okay. So, then the generation part would be like this. So, delta Gj for component J, the total generation within that specified volume small v equal to this. So, it would come like this. Okay. So, Rj into delta V. So, this part we can substitute there in this general material balance equation here, this part we can substitute here and then the general mole balance equations would be like this. Okay. So, this is the general mole balance equation. So, now if we dividing both sides this delta V both side left side and right hand side. So, then we will get this okay. And then after rearranging and taking limit means first we are dividing delta V both sides and then we are taking limit delta V tends to 0 means very small volume. So, then we are getting this differential type dFj by dV equals to Rj, these equations we are getting. So, this is the differential form of design equations for plug flow reactor for component J. If we express it in terms of component A, this is our reactant J equal to A. So, then we can express the design equation dFA by dV equals to R A. This is the design equation for or we can express this rearranging dF dV equals to dFA by R A, and then if we integrate within this ranges volume changes 0 to V means total system volume. I said these reactors from this reactors total volume, if we consider V is the total volume of the system, total volume. Okay. So, then if we integrate within that limits 0 to V, then when at just entering, so then their molar flow rate equals to 0, and when at the end of the reactors the molar flow rates of component A is this, within that limits if we integrate, and then finally we are getting this is the design equation after rearranging. So, okay. So, this is the design equation for a plug flow reactor. So, these are the things we should remember, means this is design equation plug flow reactors, and okay. So, this is in terms of means this design equation we are expressing in terms of molar flow rate F A naught F A dFA minus R A. So, here's molar flow rate, this volume left hand side is the volume of the reactor, and right hand side that is expressing in terms of molar flow rate. Okay. So, that later we can change that in terms of conversions also, means in terms of molar flow rate we are expressing, later we can express or we can change that into in terms of conversions X. So, that we will discuss later. Next is the packed bed reactor. So, this is the continuous also flow reactors. Here's right hand side you can see this is a packed bed reactors. Here's packing of catalyst is there inside of the reactors. This is the catalyst tubes or catalyst bed is there. So, here's we are maintaining some temperature, constant temperature or pressure inside of the reactors, and then means by passing the coolant in and coolant out. So, isothermal temperature will be maintained inside of the reactors. So, then if we pass the feed from the bottoms and we will get the product from the reactors once reactants will pass through that bed, catalyst beds. So, this type of reactors catalyst means that we are using amount of catalyst may be used, that may be 1 kg, 2 kg, 10 kg in terms of kg. So, here we are not expressing anything in volume. So, whenever packed bed type of reactors in terms of weight W. Okay. So, here the rate of reactions for that type of reactors RF minus RA primes we have to use RA minus RA prime. Whenever it is here the unit of this R minus RA prime or rate for this type of reactors, each mole of A reacted per unit time per gram of catalyst or per kg of catalyst. If we take kg of catalyst, then that we can express in terms of kg catalyst. So, it is the rate when we are using packed bed reactors and catalyst we are using solid materials, then in the rate expression that will come. Otherwise, in case of the CSTR or plug flow reactors, that rate would come moles of A reacted per unit time per unit volume there is importance. So, therefore, that type of reactors we whenever we will design the volumes we will consider, and in this type of reactors we will use only weight of the catalyst or amount of the catalyst is required for to design this type of reactors. Okay. Similarly, here's this is we have shown here, means just schematic diagram of this type of reactors we have expressed. So, here we have taken that catalyst, this is the catalyst bed or small elements we are considering, that is the delta W that we have expressed here. Delta W quantity of the catalyst we have taken at this particular point, molar feed rate, that is the FAW, and at this particular point we are expressing at delta plus W plus delta W position or location. So, molar flow rate or feed rate is this FAW plus delta W, and here the generation is delta GA, that is the generations. Rate of generation means the component A or Jth species that would be decomposed or disappearance or generated inside of the reactor, that will consider. So, then this type of reactors if you do the material balance, then inlet, outlet and generations and accumulations part. So, since the reactor is steady state, so then accumulation part will make it 0, and then at steady state. So, FAW minus FAW plus delta W equals to RA prime into delta W, that is the generation part. And then if we divide left hand side of this equation and right hand side of this equation by delta W, and then taking delta W tends to 0. So, then the equations after rearranging, so we will get dFA by dW equals to RA prime. Okay. So, this is the differential form of design equation of packed bed reactors. This is the consider you can continuous flow reactors, packed bed reactor. So, here this is the differential form of the mole balance or design equation for this particular reactors. So, here if we know that this is equals to F A equals to F A naught minus F A naught x. So, F A naught, that is the amount that is in, and F A that is out from the reactors. So, means difference between this would be the amount that component A reacted, means consumed during reactions inside when that reactant present inside of the reactor. So, that part would be the means F A naught minus F A, the difference would be the amount consumed or take part in the reaction, that would be F A naught into x, x is the conversions. Okay. So, then if we differentiate this, we will get dFA equals to minus F A naught dx. Okay. We will get this. So, now this equation we are just rearranging, and then we are substituting these parts, or first we can integrate this with respect to the total system weight of the catalyst 0 to W. Okay. W is the weight of the total weight of the system, means here you can see, let us say from here to here. So, total amount of the catalyst that is required, W kg of the catalyst is required. Let us say to fill up the reactor to get a specified conversions. Okay. So, if we want to get, let us say let x equal to 10%, 20% conversion. So, then we have to specify that particular conversion. So, then the total amount of catalyst you have to place to carry out the reactions that we can easily find out. So, here we are integrating this, and then left hand side we are getting W and right hand side we are getting this, and here W dFA whatever we are getting, that we can replace with this. Then the rate equations, the design equations will be expressed in terms of, here design equation in terms of molar flow rate, here design equations expressing in terms of conversions. So, W equal to F A naught, F A naught we can place inside or outside also, means integrating 0 to x F A naught dx by minus R A prime, this way also we can write. Okay. So, F A naught, that is the constant, so that we can take out from the integrations inside or outside, either way we can express. So, this is the design equation for packed bed reactors. This W we can calculate once we know x is specified. Let us say we need 80% conversions. For 80% conversion x we can put 0.8, within that if you know these are the components. So, that we will discuss later. So, the use of design equations, what are the use of this particular design equations. At the beginnings in our last class we have discussed the design equation for the batch reactors, that is in the differential form, that is minus dNA by dt equals to minus RA into V, we are expressing in terms of component A. Okay. So, this is the differential form, and if we integrate this differential form after rearranging, so T is there. So, left hand side we are getting T, and right hand side expressing in terms of conversions. Okay. 0 to x A Na 0 dxa by minus R A into V, this is the integral form of design equation for batch reactor. Similarly, design equation for CSTR we have derived or we have developed. This is algebraic form of design equation, that is V equals to F A naught minus F A by minus R A, or we can say V equals to F A naught minus F A equals to, since here this is F A naught minus F A equals to, if we take this, that would come F A naught into x. Okay. So, that we are replacing here or substituting here, then V equals to F A naught into x if you know the conversions, and minus R A rate of the reaction. So, then we can easily means express this way, or either way we can express if we know the conversions, then we can put it that x value over there. If you know F A value, then also we can use this equation to find out the volume is required to get a specified conversions for that particular reactors when we are using for a specified specific reactions. If we choose that particular reactor, so then what would be the required volume that we can decide or we can design that reactor. Similarly, for plug flow reactors also it is the dFA by dV equals to RA, that is the if we integrate that or integrating forms that we have derived this, or we can express this in terms of conversions also, or we can use this way also the design equations we can express V equals to Fa naught 0 to x a Fa naught dxa by minus Ra for plug flow reactor. Similarly, for the design equation for packed bed reactors also we have discussed. So, dFA by dW equals to Ra prime, and then integrating form of W equals to Fa to Fa naught dFA by minus Ra prime. So, that is the integrating form of design equation for packed bed reactor. So, if we express in terms of conversions, so then W equals to, we are getting W equals to 0 to x Fa naught dx by minus Ra prime. See, here we are using Ra prime, here we are using Ra. So, this is the basic difference, means from plug flow reactor and packed bed reactor. You should remember this, means when we write a design equation for a plug flow reactor, packed bed reactor, these are the basic difference we should keep in mind whenever we write the design equation for that particular reactors. Okay. So, if we know that how much conversions, let us say 80% conversions of a reactant we want to get, and for that we have to design a packed bed reactors. So, then how much amount of the catalyst we need, means weight of the catalyst, that we can easily calculate, means theoretically, and for that reactions, for the reactions we have to know reaction, these are the components, means minus Ra prime, that we have to know, and Fa naught we have to know, xa value 0 to xa value we have to specify. So, then amount of the W or amount of the weight of the catalyst is required to conduct the reactions and to get that specified or desired conversion, we can easily evaluate or calculate for that system. So, these are the summary of what are the things we have studied or we have discussed so far. These are the summary, means design equation developments for that all type of basic reactors, batch reactors, CSTR, plug flow and packed bed reactors. We should remember or we should note it carefully. So, these are the things would be useful whenever any other type of reactors we want to design or to get the design equations for that particular reactor. These are the design equations would be useful, very useful. Okay. So, today is up to this. So, in our next class we will discuss something else or something different things. Okay. So, anyway, thank you.